Or I look and I see something that I didn't more than about 6 months ago. Yes, I think
Thanks for coming. Pleased to see you. So, some of you may have developed an idea that semester is over. There are boring and necessary mathematical tools that no one needs, and I will just pay my time to the class, but you will do nothing, and it will be fine to finish. I just imagine myself in the class what I was doing as an undergraduate. But I invite you to wake up today. Well, you do not need to do it every time, because for a reason. Last about 3 weeks, we did a lot of mathematical rigor and details for harmonic oscillator, which is a little above of minimal necessary things. I hope it leaves some positive impressions, skills, and traces in your memories for next things, and maybe for someone it will be helpful for scientific career or educational career. But what we are going to do today, we are returning back to the very basic level. And what we will do today will belong to the two-dimensional rotations. We will return back to Bohr's model. If you are planning to pursue a career in teaching, this is some minimal amount of information that is typically exposed to school kids or college students. So, and I was thinking, I should admit, I wasn't preparing as deep as I should, but I was just thinking what to tell. And I found a characterization of today's meeting. It is a fairy tale for adults. So by the level of mathematical rigor, it will be something really easy. So I guarantee you 200% that each of you can stand up, just go over slides without preparation and explain each step. So my role is very auxiliary, just to flip the slides. But behind this simple derivations, there will be deep fundamental ideas that are applied again and again in more advanced topics. So if we need to get these ideas, we do not need to torture ourselves with complicated mathematical things. So I will start from the beginning in a few seconds, but just giving heads up, there will be, well, several concepts. One of them is transition from rectangular to curvilinear coordinates. This is part of calculus 3. In different colleges it is different. And this is like differential geometry, non-Euclidean spaces. We do not get so deep. We will touch only polar coordinates that you already know. But this idea about polar and later spherical coordinates is belongs to like core minimal knowledge of human society, because the simplest practically useful problem, hydrogen atom, cannot be solved mathematically without this concept of curvilinear coordinates. I do not believe that we will have time until the end of semester to study step by step for solutions of hydrogen atom. I will just declare them for the lack of time. But the fundamental concept that is behind will be part of today's meeting. And I will attract your attention and show special sign, like wake up twice, look here. Another concept, you are already aware of degeneracy, right? We talked about it when there was a multidimensional boxes, right? Like 3-dimensional, 2-dimensional. There are several states which have the same energy, but they're different quantum states. In the problem today, Bill show another example of this degeneracy concept. And it will appeal to your fundamental background knowledge about like hydrogen atom when there are 3p orbitals which have the same energy, right? 5d orbital. So something in today's material will focus our attention to the concepts behind it. Curvilinear coordinates. And there will be a promise of connection to experiment. I will not fulfill this promise today. We will probably postpone to the next meeting, but I will pave a way of connecting between rotations and the true experiment that can be done. Maybe you will be doing this experiment in PChem labs next semester. Well, let's talk about projects and the evening. Just yeah, evening. So a little promise: if your resources of internal resources of alertness are limited, keep relaxing. I'll give a sign when it will be really important. This is yet on the motivation. So if you look into Wikipedia on rotational spectroscopy or any text related to rotation spectroscopy, you will see a comp, a spectrum that looks like 2 ounce with peaks at the equal distance but different intensity. And it is typically what happens if you do have a diatomic molecule in vacuum and one probes it with like infrared spectroscopy. Just looks how it is able to absorb at different frequencies. So the diatomic molecule can oscillate because it is oscillator around equilibrium, and in addition it rotates, right? Surprise, surprise. Quantum features are exhibited for electrons that come close or far from positively charged nuclei. No problem. Quantum properties are manifested when 2 nuclei oscillate. You also looked at this idea for the last 3 minutes. And today's surprise is that if an object rotates, just, you know, take a plate and try to smash it into the wall, while it rotates, it may exhibit quantum properties, especially if it is on the angstrom size. And if anything has quantum properties, means that energy states are quantized. And if you look for spectroscopy, there are transitions between these levels. So the idea that we will develop concepts to understand is that this is U equals 0 absence of oscillations. So it's the oscillatory degree of freedom of diatomic molecule is in the ground state. This series of states is when it is in the first excitation. I wouldn't show it as moving fist because it's more like 2 hump camel. But for each of these vibrational states, there are additional substates, sublevels, corresponding to rotations. The rotation of atoms on diatomic molecules, even rather heavy, much heavier than an electron, it still has quantization. And for speaking about spectra of diatomic molecules, one needs to take into account these quantum features and transitions between ground and excited and different sublevels. And there are some symmetries, some properties. I think this is hydrophilic acid. One is getting rather symmetrical features, and based on the spectral symmetries, one can discriminate analytically which diatomic molecule is in the container. If you have mix, then it will be overlapping with same style but at different frequencies. So if you have unknown products of reaction, you can identify without touching. So a little motivation connection. Okay. Keep sleeping. Do not focus. I'll tell when it will be something. So this levels, now I'm declaring without giving exact solution. So it doesn't have. There are sub-levels for vibrations, there are indices for quantum numbers, and there are specific symmetries for transitions between them that give this fix. And I think we will return to this slide either by the end of this meeting, which is unlikely, or in the middle of the next meeting. So since the sub-levels for rotation are offsetting from each other on rather small energy values, smaller than room temperature, there is a new phenomena that you all are aware of based on your background education and skills. But we never pronounced it out loud in this class. So if a system, it doesn't need necessarily to be quantum, but a special quantum system, is left alone, isolated, 0 Kelvin, it will stay in the quantum state in which we prepare it forever. Ground, if it is in ground state, it will be in ground state. We prepare an excited, it will be an excited. This is somewhat light because nothing is isolated. But if we are narrow followers of the paradigm of like statements, postulates of quantum theory, it should be this way. Nothing is isolated. Nothing is at 0 Kelvin. Typically, any object is at room temperature, or if you want to have it a little cooler, it's at liquid nitrogen temperature, which is also not an absolute 0. And there is a phenomenon that is too hard for us to process mathematically right now. We will just accept the phenomenology of it. Through different motion in different degrees of freedom, there is a thermal excitation from ground to excited. Not 100%, a small probability, maybe 1%, 5%. So there is a thermal distribution. If there are several levels, the lowest one is occupied at most. Next will be a little less, right? And in order to reproduce this comp looking spectra for rotational spectroscopy, one needs to take into account that several rotational sublevels are occupied. And they are occupied according to Boltzmann distribution. Right now, it's not our main focus. I'll try to briefly cover it after there are several things and they need to arrange them. The main goal is to get the spectrum and ideas behind it. The exact reproduction spectrum is not the goal of this class, but we will try to move in this direction. When you will be dealing with chem2 next semester, equations like this, using Boltzmann distribution, non-zero temperature, and plugging in energies that are obtained from quantum theory will be a substantial part of the next semester. So just giving you a little heads up, and considerations like this one will be repeated again and again. And this comp structure gets, because there is a degeneracy which grows, and there is a energy in the negative exponential, there will be trajectory trends, one to grow, one case, and another to drop. Right? You have these two wheels going up and going down. Okay, I think this is a goal that I want to achieve through this consideration. If we get to the slide today, I will be happy. If not, it will be normal. So, through our consideration, we will get an idea that rotations can happen in different directions, clockwise and counterclockwise. Okay. It's not a big surprise. Rotations can happen with different angular speed. But this value of angular speed will be quantized. Positive and negative. Depending on the angular speed, the energy will be growing, approximately quadratic. And the higher the speed of rotation, the higher the energy. Plus, for specific absolute value of this rotation, there will be several states with the same energy, but they will have different quantum numbers. So there will be degenerate. Several states, degeneracy number. And if this information is plugged in, offsets between states, into typical expression for spectra, I need to spend time on introducing this equation as well, which is another concept. Fermi will be ruling. Then one will be able to get this count. So, rotation quantum number, energy, degeneracy, and offsets. Okay, now we actually start the meeting. And it is recommended to wake up at the orange level, not yet to the red. For Amelia, it is next couple of slides are critical. It's basically your project. So the concept of quantized rotations is applied to a range of objects, either to diatomic molecules that are rotating, or just electron in the hydrogen atom, or in any other atom, right? We are oversimplifying this problem and looking through the rotation in one plane. Because in our common sense, rotations of two objects happen in one plane, like planetary systems, Earth around Sun, or Moon around Earth. So it's like everything in plane. In quantum world, there are deviations from this, and we will consider them later. Now let's just follow this planetary model for simplicity. Otherwise, we just throw all off the head. So, electron, nuclei, distance, angle. Right? I don't know how to introduce it better. Just dry definitions. Now, we get used, it's our custom to quantify motion by the length of trajectory, odometer. If I have, well, I do not have it, but some colleagues and students have this wrist devices that count how many steps you do or how many miles you went through. So trajectory in length units. Can we use this concept of length units for rotational motion? We can. So you can just walk, use this stick that walks together with electron on the this circumference on this arc trajectory. And then if you start from 0 angle, as far as it goes to this point, you can measure the arc length of this trajectory. If this arc length is, if the angle is small, arc length is small, how can we find it? What is this length if you know the distance and angle? Do not look, the answer there is already with approximation. Just use your common sense and knowledge of Pythagorean theorem. Huh? If we have the rectangular triangle, we have two short things and one long, and we know this distance, and we want to know the side that is opposite to the angle. Sine. So r times sine phi. But if we take Taylor expansion of sine, and you all were taking some calculus 1, 2. So Taylor expansion of sine is x minus x cubed over 3 and blah, blah, blah. The first term is x. And if the angle is small, then sine phi is replaced just by phi. So if it is infinitesimal angle, and this is infinitesimal side of a triangle, then the side, instead of side will be equal r times d phi. Instead of sine, it is just phi. So infinitesimal is okay. And from common sense, without any differential tricks, what is the length of the full circle, of the radius r? 2 pi r. If it is less than full, then it is r times angle, or angles in. But if you take this connection between infinitesimal arc length and the angle, then we can divide both sides by the arc length. So d phi over d L will be 1 over r. Okay? Truth. No cheesy truths. Be careful. Just I'm not going to lie. I'm not intending to do errors, but just if you find some. Suppose that we have two-dimensional motion, so that electron can be located anywhere on the plane, at any distance and at any angle. And wave function will depend on this theorem. And suppose that by some reason we need the derivative of wave function over this length, because the length, the distance, is the only thing we know how to do this. So we apply rules for differentiation of the function of two arguments, for the two terms, and then there is a chain rule, right? So we take derivative over this variable, and then we make the ratio of the variable function depends on and this arc length over which we find, right? This is permitted trick because if you cancel dr here and there, it will be d psi over dl, right? And here we do the same trick. So we need deep psi over dl, but we put it as deep psi over angle, and then angle over length. Now let's do an approximation for a time, not forever, that we forbid our electron to depart from the orbit, that it will stay on a certain distance. This is not quite correct, but it will be legitimate to get the concepts, because otherwise you will just bury it under mathematical detail. So suppose that distance doesn't change, then derivative of psi over distance increments will be 0. Then we will have only this term. And then derivative over arc length will be equal to derivative over angle with this metric coefficient, 1 over r. So now please wake up and observe the concept. The same concept is it's one of the major concepts of multidimensional calculus, of differential geometry. When you transfer between different system of coordinates, especially from rectangular to curvilinear, then derivatives are obtaining like metric functions, metric elements in front of derivative over other variables. Why it is important? Why this concept is mathematically fruitful? One cannot solve for hydrogen atom without it. And another thing, the derivatives are typically entered into Hamiltonian when we do quantum theory. And if we follow this way, then the Hamiltonian differential Schrödinger equation that we need to solve will include additional terms. That brings math on the next slide. This trick with transition between different system of coordinates will be responsible for competition between centrifugal and centripetal forces. If you read the biblical story about Goliath and David, there is this device to throw things far away. On the arm you put mass. So, or when you just put something on the rope and try to rotate, there is one force makes it to depart, another force on the rope makes it to keep. So this transition between differential operators will be responsible for this effect later on. Okay, you can take a nap for important progress. One important part of that. Please give me signs in form of raised hands if you were taking any level of physics at college. Good. Please give me the same sign if you were exposed to the concept of angular momentum anywhere except this course. Okay. So I will not question you, I'll just repeat, but having in mind that it is not a new thing for you. So if an object rotates on the circle at a distance r with momentum p, then this motion is described with angular momentum, which is a vector outside of this plane. Right? And there one uses the cross product at quicksand, right? So basically, it is what we are doing. And in case all angles are rectangular, if momentum is perpendicular to position vector, and angular momentum is perpendicular to other two, then absolute value of the angular momentum is just product of distance and momentum. If they are at an angle, then there will be sine between them. If they are oriented in space, there will be like metrics for cross-plotting. But now we don't. So let's open this simple expression with all deep knowledge that we had from previous slide. Distance is distance. But momentum is, what is momentum? According to material that we were chewing through several times in this course. Huh? It's more like a transition between velocity and momentum, but in terms of quantum theory, which form of momentum is plugged into Hamiltonian? Differential. And you, right now, you do not need to think. You can just read. How do we define the momentum operator? Yes, as derivative over position, derivative over length, right? Yes, imaginary unit and time constant. If instead of x, instead of distance, we have arc length, it will be derivative over arc length, right? No cheesy things, pure logic. Now let's plug this red ugly calligraphy into here. So instead of minus I h bar and derivative over arc length, right? But derivative over arc length is same as derivative over angle phi divided by this multiplied by this metric coefficient because of transition between rectangular and curvilinear system of coordinates. Good? Excellent. And now we can, with calm mind and pure heart, cancel the arc here. So our journey into curvilinear universe kind of stops here. You just got exposure to the main concept, and for this problem, the mathematical complications will be behind. But be alert, either at the end of this course or maybe in other courses when someone decides to go over hydrogen atom details, this trick of going between rectangular and curvilinear will be repeated, and it will be much more complicated than here. It will be not just this stuff, it will be other stuff. So, projection of angular momentum onto z axis is minus I h bar derivative over angle. This is a big journey. If momentum is angular momentum is so simple, there is a hope that solutions to the equation in any math will be simple as well. Just because of oversimplified model. It's rare. So, if we need to describe quantum aspects of rotation, we may want to quantify measure of motion with angular momentum rather than linear momentum. But on the other hand, if we do want to play this game of operators, Hamiltonians, and so on, we need to express observable in terms of differential operators. And for differential operator corresponding to angular momentum, which is measure of circular motion, the expression is as simple as possible. Operator is variable corresponding to measure of circular motion, and quantum operator corresponding to this variable is very simple. By functional form, it is the same as linear momentum in Cartesian Euclidean space. Okay? So next step. Suppose we want to do quantum theory. The simplest thing one can do is to solve Schrödinger equation and to set up Schrödinger equation when needs Hamiltonian operator of energy. If there is no potential, there is only rotation, and by some reason, by some force, it performs circular motion, and we do not consider it by which reason. Then the contribution to energy because of the kinetic part of this motion is kinetic energy, which is momentum squared over 2 mass. Suppose you do not see this, you see only this. P squared over 2m, where P is momentum corresponding to this arc length. Momentum that is yet Cartesian and perpendicular to radius. Good? No light, no good. P squared over 2m. No, one can multiply and divide by the same arc. Problem, right? Now, on the numerator you have P squared, R squared. Can we combine them as P times R? Right? And the square we will also. Good. In the denominator, you have mass times 2 mass times R squared. Good. Also no tricks, some definitions. So what is here up front is angular momentum squared. So kinetic energy of circular rotating particle is angular momentum squared over mass and radius squared. Good. What we did right now works also for regular classical mechanics for physics without any quantum properties. If something is rotating, then there is an analogy for linear translational motion. Momentum is measure of motion, mass of measure of inertia. Like if a heavy truck bumps into a wall, it's likely to break it. If a skater will bump into a wall, maybe skater will suffer any measure of inertia. In rotational motion, same analogy. Angular momentum is measure of motion. Mass times r squared is called inertia, measure of inertia. How much energy you need to apply to stop this motion. And it is typical referred with letter I for inertia. So there is nothing new, it's just new notations and abbreviations which sometimes throw minds off. Nothing complicated, we just soberly follow conditions which I didn't like. And it was on the other side of the world. So angular momentum squared over 2 inertials. So if our angular momentum is derivative over angle, then kinetic energy will, and we'll take square here, square of imaginary unit will be -1. Okay. Minus times minus times minus will be minus. Okay. 2 minuses cancel, 1 stands. And then Planck constant squared to inertia in the denominator, second derivative over angle. Please accept Hamiltonians. You got Hamiltonian for Bohr model. So it is curvilinear motion with the only variable that determine it is angle, if the radius is fixed. it looks very much familiar to what we had for particle in the first case. Right? Second derivative over independent variable with some constants up front. Before it was like Planck constant in two masses, now it's Planck constant in two inertias. But other than different letters here and there, it is the same, which means solving it will be much more complicated. Okay. Please consider to wake up with the orange color. There will be a constant. If you have an operator in the power n, then these two things will commute to give 0. Right? Like if it is x, and this will be x squared, then it will be x minus x equals 0. If it is L sub z, z projection of angular momentum, if it is Lz squared and Lz, it will be also commutative. But the Hamiltonian is composed of only squared of angular momentum. Hamiltonian commutes with angular momentum squared. And since Hamiltonian is composed as Lz squared, it should also commute with Lz in the first power. Right? So we can derive a conclusion. If two operators commute, they share the same set of eigenstates. Okay? And if they share the same set of eigenstates, why should we solve the one which is more complicated? Let's solve the one which is more simple. So instead of finding eigenstates of Hamiltonian, we can find eigenstates of L sub 0 period, which is simple to the death, just one derivative. But because of this commutation stuff, eigenstates of Lz operator at the same time will be eigenstates of Hamiltonian. And also eigenstates of Lz squared will be eigenstates. But it paves a way to do simpler things first and compose more complicated sets. Find eigenstates of angular momentum projection. Believe that they are eigenstates. Okay, important information is done. Now we'll reduce the level of error. Do not do this. Don't do this. Let's continue a little bit further. We still have 4 minutes. Okay, we are trying to find eigenstates of this operator, minus I h bar dt5. Our wave function psi depends on phi. You are coming to the university to make combinations of root vectors. Psi of phi. What else do you need? So psi of phi will be eigenvalue equals to psi of phi. And no one can forbid us to divide both left and right by h bar. So that on the left we will have the just derivative, and on the right you will have the ratio of eigenvalue of angular momentum to the Planck constant. Why do we do it? Angular momentum has a dimension, like distance times momentum, which means distance times mass times distance divided by So if you do this ratio, the result will be dimensionless. So this is our mathematical challenge, but I have no doubt that you can do it well. Although I will be happy to do it. So first derivative of unknown function equals unknown eigenvalue times the function. And this definition of M is that by B multiplied to one constant, it will give the eigenvalue of unknown element. So great pleasure of solving differential equations. Derivative of a known function. Divide left and right by psi by a known function. Multiply left and right by infinitesimal increment. Then on the left will be everything of a known function. On the right will be everything of the independent variable. Then apply integration to left and to right. On the left will be logarithm. Right? On the right will be just angle. And then, by our favorite tradition, we place left and right parts as powers of exponentials. So e to the power logarithm psi equals e to the power imaginary unit, this eigenvalue, dimensionless eigenvalue times n. And exponential logarithm is the function itself. Combination of Greek letters. Psi of I equals the Greek constant e to the power I and phi. Do you see any difference from plane wave? I don't. But in mathematical sense, it's same as a plane wave in the free space. Right? But there is a little difference. Free space was free, and our rotations are confined, same as particle in the box. Not exactly the same, but similar. If in the particle of the box there were boundary conditions of 0 at the edges, here it is a new type of boundary conditions. After making a full circle, wave function must be equal to itself. Okay, our time is up, and some of you have schedule limitations, so let's stop here. But I think we got all major concepts except degeneracy. Thank you for dedicating your time, and looking forward to see you on the web.